Hi there, welcome to our channel where we talk about traffic operations in practice. The overall intent of this video series is to reduce the learning curve for students and entry-level engineers by providing them free and high-quality learning materials in the field of traffic operations, including highway safety and travel demand modeling. The majority of content in this work is written by Professor Jiangling. My name is Amit Kumar Singh. I'm one of the contributor of this work. I'm a licensed engineer in the state of Texas. I received my bachelor's from IIT Bombay in India and my master's from UT Austin in US. Other three contributors of this work are Priyanshu Singh, who works in the field of artificial intelligence, Nidhi Kumari, who has a background in computer science and is a programmer, and Namrata Kumari. She has a background in electrical engineering and currently she is working as data scientist. Now let's get to the main content. Let's get started with chapter 2 of basic concepts in traffic operations. Till now we have been mostly discussing the theoretical aspect of traffic operations. So mostly what is the intent of this work and uh, what kind of work we do as a part of traffic operations. This is the first technical video where we will be discussing the technical work we need to know as a part of traffic operations. So chapter 2 focuses on the basic concepts of traffic operations. This is probably the first and only chapter which is kind of a bridge between academia and practice. So in this chapter we will look at some of the concepts, mathematics, a lot of stuff we actually learn in our undergraduate and masters. So a major portion of this chapter is kind of an overlap between academia and practice, whereas the other chapters there that will be more focused towards the practice side of things, and concepts presented in this chapter are selected such that all the concepts are used in day-to-day life of a traffic engineer. So everything we are going to discuss under this chapter are the selected concepts which are usually taught in undergraduate or master schools but are heavily used in practice. So the format of this presentation is on the left side. I have the actual material, or let's call it book, and on the right side I will be drawing and explaining certain things. So the way I wanted to have this format is on the we are not going to learn everything at one time. So as we know, technical stuff take several iterations to learn. So the way I envision it is to explain things while on the left hand side the page where we are referring is open. So uh, somebody who needs to learn and understand these things has to go through videos and then has to go through the book and then come back to video and has to go through the book again. So there will be several iterations of learning. It's almost impossible even after years of experience to capture and learn everything at first go. So I have the book or the material with page number as it is open on the left hand side so that we can facilitate that learning. So when we are watching the video we can relate where in the those big pages where that material lies and which text I am referring to. So on the left hand side this is the actual PDF, and on the right hand side I will be explaining certain things if I have to. I'm drawing with my mouse. In future, if I can, I will use a touchpad, but for now let's go with the mouse and I'll try my best to draw it as realistic as possible. So let's get started. The first things we need to know is traffic flow theory. So flow rate. Flow rate is the number of vehicles that passes through a given point on the roadway. Uh, that's pretty much how flow is defined. Even in the fluid mechanics is the volume that passes through the passes through one point. So on the roadway, the number of vehicles that passes through a single point is called flow rate and is usually denoted by Q. So now the flow rate in traffic operations is usually referred to using the term volume. So from here on after in the videos and in the text, if we are looking at a word volume, that means flow rate. It's not the physical meaning of the volume. So in physics we learn that volume is kind of a 3D space. For example, if this is a cube and this edge is A, then the volume is A cube. Is the physical space that is occupied by certain material is volume. However, in the world of traffic operations, volumes means flow, is number of vehicles that passes through a certain location within a given time. So that's the volume for us, and it's referred here. The second one is density. Density is the number of vehicles occupying a specific length on the roadway. So the way density is defined is this is the roadway, and if we take a snapshot of this roadway at any given time, then the number of vehicles within that particular length is called density. So the number of vehicles per mile is called density. Speed. Speed is another important aspect. So the speed of individual vehicle is the distance per unit time. Since high school we know how to define speed is the distance per unit time. However, in traffic operations, volume can be exactly defined and density can be exactly defined, but it's kind of difficult to define the speed. So volume is we look at how many cars passes through certain point in 1 hour, that becomes our volume or flow. If we take a snapshot of a roadway, then we can have a look at how many vehicles are there within a certain distance, and then we take the number of vehicles divided by the roadway length, that will give us density. However, when it comes to speed, individual vehicles have different speed when they are traveling on a roadway. For example, let's say there are three vehicles. Now this vehicle can be traveling at 55 miles per hour, this vehicle can be traveling at 60 miles per hour, this one can be traveling at 57 miles per hour. Now if we are trying to define the speed, then now we have three speeds here. So that's one situation. Another situation, this is the variation of speed in the space. Now another situation is this vehicle, let's say this is vehicle number 1, vehicle number 2, vehicle number 3. Let's say vehicle number 1 was traveling at 55 miles per hour. After few seconds, vehicle number 1 started traveling at 50 miles per hour. And then after few seconds, the same vehicle started traveling again at 54 miles per hour. Now if we are trying to define a speed over a period of time, we noticed that the speed is not constant for different vehicles, is not the same, and speed is not same even for the same vehicle, it changes over time. So several statistical methods are available to estimate an equivalent speed. Let's call it equivalent speed. So depending on what method we are using, we will end up with a different definition of speed. So let me scroll down a little bit. So one of the method of aggregation is called time mean speed. The time mean speed is the average of all vehicles passing through a certain point. So if we stand here and see uh, how see how many vehicles passed and what is their speed, then the time mean speed will be defined as the sum of all the speeds divided by number of vehicles passed. So this is the time mean speed. Time mean speed is simply the average of speed of all the vehicles that is crossing one single location. This mean speed is measured in the field using something called spot speed study. So usually there are automatic radars, or there is a person with a radar gun pointing at vehicles, and then they figure out what is the speed of the vehicle. So usually it's automated, where there is a sensor which figures out the speed of vehicle. Then the second one is space mean speed. Before moving forward to space mean speed, I should mention that Even though we study this spot speeds or time mean speed, this is hardly used in practice. So time mean speed is measured in the field as a part of speed studies. So speed studies are done to do several kind of small traffic studies. However, time mean speed is rarely used in traffic analysis. Now the second one is space mean speed, which is frequently used in traffic analysis. So the way space mean speed is defined is the average speed of the vehicle through the space. So space mean speed, the way is defined is the total time taken, average time taken by different vehicles to cross certain length, and then so the way space mean speed is defined is the average time taken by different vehicles to cross this stretch of roadway, and total taking the length of the roadway and dividing by average travel time. Average travel time. That becomes the space mean speed. Is also given as this formula. So we have learned about this in probably third year of our undergraduate, again third year, fourth year, again we repeat this in masters again. So these are some of the concepts that are used in practice. So for example, a flow rate is heavily used in practice. Density. Now speed is defined in different way. One is time mean speed, which is used in traffic studies but only few times. And then the second one is space mean speed, which is heavily used in traffic operations. So the speed for calculations within traffic operation is the space mean speed, like I mentioned. Space mean speed can be directly measured in the field by calculating time taken by vehicles to traverse a given roadway length. With the advancement of vehicle probe data technology, this is GPS based data, and big data analytics, the speed and travel time can be easily collected and used for large roadway networks across the nation. So usually for space mean speed, now with the big data technology and everyone's cell phone and everyone's car having the GPS data, we do not have to go and collect the space mean speeds. So what we usually do is we have GPS based data and we figure out what the timestamp is when vehicle is here, then what the timestamp is when vehicle is here. That gives us the travel time of vehicle number one. Then we do it for multiple vehicles, so let's say call it travel time 2, and then now we know the length divided by average travel time. That can give us space mean speed. And since the GPS based data come in a consistent format, we don't need to calculate it for different roadways. There are big data analytics tools that can calculate the space mean speed for every roadway in the nation. So several commercial resources are available that provides the space mean speed for almost every roadway and they provide it by any given time and date. So as we know that speed changes based on time. During rush hour the speed on the roadway are lower, so and maybe during the holidays, let's say the speed, there is a congestion on the roadway and then the speed is lower. So this GPS based data can provide a space mean speed throughout most of the roadways in the nation, and we can choose any date and time to collect that data or to use that data. So two commonly used online resources that are used is NPMRDS, which is also National Performance Management Research Dataset. This is a free data source from FSWA. So if we are working on State Department of Transportation projects, then we can request an access through our client to get access to this data set. And another one is NREX. Several Department of Transportation has contract with NREX company, so we can get their space mean speed or space mean speed or average travel time data and congestion data. For example, Texas Department of Transportation in 2022 has a contract with NREX, and if we are working on any Texas department project, then we can get access to this database. So There are several sources available. NPM RDS, if you are working on State Department projects, we can request access to it and there is no cost to it. NREX is a commercial software. Uh, if we want to buy this data by ourselves, there is a price to it, but most of the state DOTs have contract with NREX and we can directly access the data sets. So these two are very good resources to get the travel time data in real life. Next one is design. Design speed is the speed which is used in the roadway design. So pretty much all the calculations that are associated with Green Book, ASTO Green Book, we use the design speed. Then there is another kind of speed called speed limit. Speed limit are legal or regulatory maximum speed at which road vehicles are permitted to travel on given stretch of roadway. Although there are numerous factors that affect how we set the speed limit, usually the speed limit from traffic studies can be set at 85th percentile. So let's say there is a roadway and there is no speed limit sign and we have to set the speed limit. What we do is we go out in the field and do a spot speed study and calculate the 85th percentile speed and then round it up to nearest 5. That's how we set the speed limit. However, for majority of the cases there are local guidelines, local preferences. Let's say in certain area the arterial speeds are usually 35, then the speed limits are automatically set to 35 without traffic studies. So speed limits cannot be posted in the excess of legislatively mandated speed limits. So there are legislation literally set the speed limits. We cannot set arterial speed to 60. So there are legislation on what kind of roadway can have what kind of speed. That's how the speed limits are set. Now let's look at free flow speed. So free flow speed is the average speed of the vehicle on a given roadway segment when the drivers are free to drive at their desired speed and are not influenced by presence of other vehicles or traffic control devices. So this definition of free flow speed is coming from Highway Capacity Manual. Free flow speed is considered as the theoretical speed when both flow and density are 0. So there is a mistake here. This should be flow and I will correct it in the text in the PDF. So free flow speed is the theoretical speed when there is no one in the road and vehicle is kind of free to drive at their desired speed. That's the free flow speed, given the posted speed limit is still there. In practice, the recommended way of collecting free flow speed is to collect the speed of the vehicles when the flow is less than around 200 or 300 vehicles per hour per lane. So in practice, if we are observing a speed when the traffic conditions are such that the number of vehicles per hour per lane is about 200 or 300 vehicles per hour or lower, then we call that speed free flow speed. However, because of time and budget constraint, we hardly go in field and collect the free flow speed. What we do is we deduce the free flow speed based on the speed limit. So as a rule of thumb, when speed limit is less than 45 miles per hour, then free flow speed is posted speed limit plus 5 miles per hour. This is what we typically use. If the speed limit is greater than 45 miles per hour, then we use the posted speed limit and the speed between 5 to 10 miles per hour. So if we have to deduce a speed limit, a free flow speed based on the speed limit, let's say my posted speed limit is 55 miles per hour, then likely I will use the free flow speed at 60 miles per hour, given that the posted speed limit is usually around 85th percentile. So in practice, we do not go and collect this speed and we do not use the speed limit as the free flow speed. We increase the speed limit considering that there are a lot of vehicles that go above the speed limits, especially in the state of Texas. A relationship between speed, volume and density. So given any 2 out of 3 traffic characteristics, the remaining traffic characteristic can be calculated using fundamental relationship. So when we are looking at equation, there are two kind of equations we will be primarily looking at. First is statistical. Let me choose a color here. So first one is statistical, which is around 90% of equations we use in our traffic operations. And the second one is fundamental or mathematical. So mathematical equations always hold true. Mathematical. So mathematical equations are, by definition, they are always universally gonna hold true. They are not based on data, whereas statistical equations are based on data, and very few equations we are gonna see in traffic operations are gonna be mathematical equations, and this is one of them. This is a fundamental relationship between speed, flow, and density. Flow is equal to density multiplied by speed. This is a fundamental or mathematical equation. However, this is kind of a rule of thumb equation, or we can call it statistical. And most of the equations we will see later on in the video series or in our field of traffic operations are statistical equations. They are derived based on the best fit of data or doing some kind of statistical analysis on data. So many statistical models has been developed to understand the relationship between speed, volume, and density based on widely used statistical model, which was developed by Greenfield, which we learn in school or universities. Speed decreases linearly with density. So that's the graph number one. So the graph number one is, I will draw it here. So this is my speed versus density curve, and speed is linearly decreasing with density. So the Greenfield model assumes that the speed decreases linearly with density. So when density is 0, then the speed is near free flow speed. So you'll notice on the density axis, when the density is 0, the speed here is free flow speed. And when the speed is 0, the density here is called jam density or Kj. We typically learn this in our undergraduate, but in practice, one thing to remember is a typical value of jam density is 180 vehicles per mile per lane. We use this value in the highway capacity analysis as a default value. So a typical value of kj in practice to remember, or it comes with the software default, is 180 vehicle per mile per lane. The second curve shows the relationship between flow and density. In academia or in master's class, this is a very important curve. This is flow versus density curve. The slope at any given point gives the instantaneous speed of the shock wave. If we connect any point on the curve to 0, then that slope of this line gives the average speed. The slope of the curve at point 0 is known as free flow speed, and if we calculate the average speed at the center of this equation of this curve is a parabola. So if we calculate the slope of this line connecting to 0 to the center of curve, then this is called optimum speed. So optimum speed is the speed at which the flow is maximum. So if I can draw this parabola again, corresponding to this, when density is 0, our speed is free flow speed. It starts like this, and then at half of the density here, exactly at half, because this is a linear relationship, then by multiplying here density versus speed. So if we are changing it to flow, so flow is equal to density multiplied by speed. So if we change this speed, there is a linear relationship between speed and density, and if you are trying to calculate flow, so let's say speed is equal to minus k time density minus a time density, where a is the constant. Then if we are trying to calculate flow, then flow will be equal to speed, which is minus a times d, and density, which is minus a d square. So as we can see, in simple terms, if the speed and density has negative linear relationship, then uh, the graph between flow and density will be inverted parabola. So which is like this. As we know, parabolas are symmetric in nature. So at kj, which is the jam density, here we have kj jam density. At exactly at kj by 2, we will achieve the maximum flow, which is q max. Now if we draw a line connecting 0 and maximum flow, then the slope of this line is called optimum speed. The third one is speed versus flow. This curve is barely used in practice, and we will not discuss this curve. However, in theory, there are several mathematical derivations, shock wave theory, and there are a lot of academic importance to these curves. So in masters, there are several lectures on several kind of derivations that are based on these curves. So these curves are very important in academia as well as in practice. In practice is more simplified than academia. Capacity of a roadway is maximum number of vehicles that can pass during a given duration while maintaining the acceptable level of service. So capacity is generally expressed in terms of passenger car per unit per hour. So capacity is number of vehicles per hour for certain level of service. For example, level of service are defined from A to F, and let's say our acceptable level of service is D. So and the corresponding volume for D is, let's say, 1600. And then when we are defining, let's say, the corresponding volume is 2000. So even though 2000 vehicles can theoretically pass through a roadway in a given hour, this is not an acceptable level of service. So we define the capacity as the number of vehicles that can pass through the roadway such that it still maintains the acceptable level of service. So the capacity is a function of acceptable level of service. Travel time is probably one of the most important equation or concept in the field of traffic operations. So travel time is defined as the time it takes for vehicle to cross a stretch of roadway. So if this is my roadway, travel time is basically the time it takes for a vehicle to go from one location to another. That's the travel time. Now, as we know, if there are more vehicles on the roadway, then the travel time will go up because vehicles are kind of stuck behind each other and different vehicles have different characteristics. So in practice, we usually use a function called BPR function, Bureau of Public Road Functions, which connects the travel time on the roadway to the free flow travel time, capacity of the roadway, and the current flow on the roadway. So the travel time is given by TQ is T naught, which is the free flow travel time, 1 plus alpha. The value of alpha we will discuss in great detail in chapter 3 when we are discussing travel demand modeling, but 0.15. Then Q is the current flow. The higher the flow, the higher the travel time is. C is the capacity of a roadway, which is typically a constant number. And Q is changing. So as flow changes, the travel time changes, and the value of beta is typically between 4 to 6. Typically 4, sometimes 6, and sometimes even different. So we will talk about the alpha, beta, and other values in travel demand modeling chapter. So this is how the BPR curves look like. So there is free flow travel time when flow is 0, and it goes up with usually with power 4. Now this curve is convex. There are a lot of great implication of this curve being convex, and there are very good mathematical relationship which we learn in our master's classes. So one of the great resource I have seen over the years is a book written by Sefi. It's called Urban Transportation Network by Sefi in MIT in 1970s or 80s, that goes through the mathematical derivation of user equilibrium, stochastic equilibrium, and many other things. And a lot of these concepts hinges on this travel time being convex. So if the travel time was like this, a linear, or it might, many of the derivation might not have worked out, or if the travel time was like this, then some of the features we use in our traffic operation might not have work out the way they work out. So travel time function is one of the most widely used equations for static assignment in the software like Transcat, Cube, Visum. We will discuss about these softwares. Visum is an emerging software which is now being used by Florida DOT, and Transcat and Cube are were the traditional software that are being used for most of the travel demand model. Majority of the models in Texas are built in Transcat. Houston MPO model is built in Cube, and probably Dallas Fort Worth model is also built in Cube. So there are different metropolitan travel demand models, and they are built in different uh, platforms. So FDOT has recently switched to Visum, which is an big move from Transcat and Cube to Visum. So we will see how the future holds like in the travel demand model world, and we will discuss this at greater length in chapter 3. The next one is delay. Delay is the additional travel time experienced by the driver beyond the free flow travel time. There are several types of delay defined for a roadway. For example, stop delay, control delay, traffic delay, incident delay, and etc. So out of these delays, the most important delay for us is the control delay. Control delay is what is calculated in practice, and that's what defines the level of service at different intersections. So the level of service at signalized intersections is defined based on the control delay. Control delay is defined as the delay caused by the presence of traffic control device. We will look at the definition and the use of control delay about the intersections in further detail later on. The next one is space-time graph for traffic flow. This is heavily used in traffic software called Synchro. So when we are working with Synchro, we will see a bunch of graph like this. These are called space-time graph. What this graph represent is each line represent a vehicle. So one vehicle uh, who was here, and then it's moving through space and time. So this is called space-time diagram. A space-time diagram for a vehicle moving at same speed and same headway is presented in figure. So this is a graph of multiple vehicles with the same speed. The speed of the vehicle is given by the slope of these lines. So as the slope of all the lines are same here in this particular example, they are parallel to each other, and they have the same headway. Headway is given by the lateral distance between these two lines. So since they have the same slope, same distance, then these lines represent vehicles that are moving in the same directions with same speed and same headway. Now let's assume there is a traffic control at this location. So and the traffic control turns red at time here. So this vehicle will stop, the next vehicle will react to the vehicle in front and slowly stop, and the next vehicle will react to vehicle in behind, a vehicle in front, which is this vehicle, and stop here. So and so on. So the next vehicle will take some time and stop behind this one. There is a time delay in for the reactions to reach to the back end of the queue, and this boundary of different densities is called shock waves. So when the signal turns green, the first vehicle goes, and then the second vehicle goes, and then they slowly start to spread apart. So when there is a red phase, the vehicles are close to each other, and when the signal turns green, they start to spread apart from each other. So the boundaries of this uniform density regions are called shock waves, and if the shock wave is long enough, if the red phase is long enough, and it reaches to the, let's say there is another signal right here, and if the red phase is long enough that it reaches to the nearest signal, then there will be a queue spillback, because these vehicles will now be reacting to this signal and the queue from the previous one. So this is how the space-time diagram and this shock wave is used in the synchro analysis. So when we are doing synchro analysis and there are multiple intersections stacked back to back, then we try to make sure this shock wave doesn't reach back to the another signals and doesn't cause a queue spillback. Thank you for listening in, and we will discuss the statistical model in the next video. Well, that's all I have for this video. Thank you for your time. Thank you for joining us. And if you like it, please subscribe to our channel and share it with your friends.